so let's start. Well, and I'm living in Germany, and 20,000 there was introduced a new identity card, and that also included RFID-based identification for paying in the internet or authentication.
For all people in Germany.
For all people in Germany,
Man.
so all that got a new identity card now have an RFID identity card. Well, and to promote this thing, the German organization sponsored a lot of RFID readers. For example, there was we have a weekly journal called Computer Bild. You see on the right side, I see here, and if you look a little bit further, you see here that there is attached an RFID reader.
Oh, that came with the magazine?
It came with the magazine, and the price was €3.70.
Oh man, that's a good deal.
That's a good deal. I bought 3 copies immediately. Yeah. Just to see what is inside these readers and how is it operated. So that was one of the starting points for me to go into RFIDs. Well, and of course, first you have to open such a reader, and then you see a reader coil. That's a big coil here, and then you have some electronics here. I have seen there have been different versions, and each version contained an RFID reader IC, mostly made by Philips, for example, a PN512 or an MFRC523. And to get the hands dirty and to make some faults and errors, I eliminated the CPU and I replaced it by an AVR 80MegaAT8.
Why exactly did you do that, Martin? Because you knew the Atmel chip better than the Philips one, so you had better access.
To this CPU, and the data sheets for the RFID reader chips, they were contained on the internet, so I had a good hope to connect them together. And I knew also that the first Elector RFID readers made some years ago was also based on Philips chips. I probably could reuse some of the software and some of these ideas. Yes, and what came, or what I did then is seen here. You have the same reader coil, then here is attached the old electronics, and here is attached the AVR microcontroller, and this is a cable going to the PC. And then I started to try to read RFID tags. And one of the first informations about the identity card was that it was based on the according ISO standard, and so I said I will just try to read it in the same way as I usually read RFID tags, and that was quite successful. And then a little bit later we had a new opportunity to get a new nice test, because Elector published a new book, and that is seen here on the left side, and Jan will hold it in the camera.
Yes. We've got the copy here. It's called Catch the Sun. Catch the Sun has nothing to do with electronics by itself, but this is the world's first book with NFC technology integrated into the book. And you will tell a bit more, Martin, about NFC right now. And
what we have in the book here is just a kind of tag. That's an NFC, Near Field Communication tag. And then I wondered, can I read these tags with a usual RFID reader, or do I read a special protocol, or do I read special protocol? And I just tried it. And the first experiment showed NFC tags can in fact be read by a normal RFID MyFair card reader. That was quite a success. But now I had to analyze the information, and that is shown on the next slide. Well, first of all, what you get is on the upper right side a hex dump with the data that is normally stored on the card in the normal protocol, and with a good eye you can see that perhaps here in this
Might
line,
be ASCII.
that might be lowercase ASCII.
Yes.
And if you go into it, you may see, oh yes, that fits nice, good. And then you have hope to decode the information. And you go into the internet and you try to recover what kind of protocols are involved, what kind of stuff is there. And in fact, as very often, you get the right information within minutes. And then it was possible to build a software to decode really the packet contained in it. For example, in a normal RFID tag, you have some information how it is organized and these blocks, and there are some magic numbers, and if these magic numbers are found, then an RFID reader says, oh, that looks after NFC, near field communication. And then you have a sort of container format, and that says there are some records written into an RFID tag if it is used as a near field communication tag. Well, here you see the first information. That's not very interesting for you, but the next block or record of information is much more interesting, because that is really the block that contains the so-called payload, the interesting information. And for example, it says that payload length is 38 bytes. It's a short record, and here at the lower line you now see really the payload. And the payload is just a link into the internet.
Yes.
First a protocol specification, and then you see that here you see exactly the text
URL.
www first NFC book of the world.
And that's, what it,
.com,
and that's what it is.
and that's what it is.
Okay.
And it's movie 2, because that is the right link.
It starts movie number 2 at this special URL. Okay.
So, in fact, with a normal RFID tag reader, you can decode also near-field communication tags. Well, that's the info slide according to that, and you may go into the detail later. What also is possible is that you can convert normal RFID tags to near-field communication tags. Well, Jan has just a normal RFID tag.
I've got a couple here.
Because Elector gave them away with
these are sticky, Martin.
Yeah. Some years ago, Elector had an RFID special issue, and every issue of the journal was supplied with one.
We had about 300,000 of these things made, and we did a small number competition with them a couple of years ago. So now you're saying
we can recover them.
I can use them as a new near-field communication
tags. Yes.
Now, tell me more about that.
Yes, we will probably have an article in one of the forthcoming issues of Elector.
Brilliant.
Well, after this quite new information, I will go back in time and cover some basics about RFID. So frequencies are normally in the low frequency region, 125 kilohertz or so, 13 megahertz. And then there are also some ultra high frequency regions, but I have not covered them yet. It's, as Jan says, shorter the wavelength, the longer
exactly. The shorter the wavelength, the longer the phase.
And I have covered the low frequency regions first, and I will go first a little bit into near field inductive coupling. Because if we are at 13 megahertz, you have a wavelength of more than 10 meters. And if the geometry of a setup is small compared with the wavelength, then you don't have to worry about waves. You just can use lumped elements, you can speak about voltage, about current, about magnetic field, and so it's just not an antenna what you use, it's more coupling elements, either capacitive coupling or inductive coupling, and normally we use more inductive coupling. Well, and I have also built a setup to demonstrate inductive energy transfer, and that can you see here. Let's go here. I have a full bridge of MOSFETs supplying energy to a coil that consists of about 20 or 30 windings, and then at a distance of 15 millimeters, that is right here, then you go to a receiver coil, and I can provide about 12 volts and 10 watts of power without problem. So that shows you inductive energy transfer, and that means you have a primary coil and you have a secondary coil, as in every normal transformer.
Yeah.
And because the wavelength is so long, we can really say it also, the RFID tags, that they built also a transformer with a coil contained in the tag reader. Well, if you have a transformer, you can build up an equivalent circuit that normally is built up of 3 components. That is a magnetizing inductance, storing the magnetic energy, and then some stray inductance that says the primary and the secondary coil are not perfectly coupled. You have some stray field.
Yes, inevitably.
And in a normal transformer, you normally only worry about the magnetizing inductance, that is very large, and you have very, very small stray inductance. In a weakly coupled transformer, such as RFID tags, you have a very small magnetizing inductance and a very large stray inductance. Well, if we say this stray inductance is very big and this magnetizing inductance is very small, you see these build a voltage divider.
Yes.
And you have only a very small voltage here. And that means the coupling is bad. To overcome this problem, a usual technique is to build resonant circuits on the primary side.
Yes,
And also
so you get some resonance and amplification.
Yes,
Signal.
yes, you can say you get an amplification, or you can also say I cancel this stray inductance by the capacitive impedance. So these two cancel out, and then I have a direct wave from the primary to the secondary. But because you have a resonance circuit, it now works only at a very narrow frequency region. That's the problem. And normally you have much of circulating currents here inside. So you have to provide quite some power here just to generate the circulating current inside this primary and to get the power really through. That limits the power in really power applications. But if we say we have a resonance circuit inside our RFID, that would mean on the secondary side, we should be able to watch it. And that brings us to a first experiment. Perhaps I should have mentioned it before. In this presentation, you will see experiments. Yeah. Several experiments and some crazy experiments, perhaps. So you will not see normal RFID readers in action, but you see other things. So let's go to the next. Yeah, there a short info slide. And that is a setup of the first experiment. You see here again the RFID card.
One of these cards, yeah.
And I have a primary coil here and a secondary coil here. And then I use a spectrum analyzer as measuring instrument, and the primary side is supplied by the energy by the tracking generator, and I use a spectrum analyzer just to display how much energy is coupled from the primary side to the secondary side. The primary coil here is built of 5 turns. The diameter is 40 millimeter and I have a distance of about 60 millimeters, so there is enough room to go inside with a normal card. And I just want to see what happens. Can I see that there is a resonance circuit inside the setup? Well, on the left side you see the response curve of an ISO 5693 so-called vicinity card. The spectrum analyzer is centered around 13.56 megahertz, so in the center, exactly in the center there would be 13.56 megahertz. And we have a span of about, I think, 20 megahertz, so to the left and to the right side we have plus and minus 10 megahertz. Yep. Well, and you really see a sharp resonant curve. That of course a little bit above 13.56 megahertz. Usually they say we tune it a little bit upwards because if we have additional capacitances
from the hand or moisture or what have you,
whatever may be
the
in
frequency
the vicinity
will drop to exactly the resonance point.
Even the housing of the RFID tag reader has some additional capacitance, and therefore you normally find
Martin, you're telling you can see from the response on your screen what type of card is involved.
Yes, you can see it a little bit, at which frequency is it. And if we go to the right screen, you see that the resonance curve looks a little bit different. It has not a such sharp peak.
Yes.
And it's from another type of card. It's a card as in the identity card, or that has been used by Electro. It's an ISO 14443 proximity card. Proximity card means they are designed that you can read them only if the reader is really close by. Well, if you could read an identity card from within 20 meters, you would say that's not so nice, because you could be spies or everything, you can be watched. And therefore these cards are, the resonance circuit is really damped. So you need more energy to power them up, so you normally need a really close by reader. And you can see it just on the resonance curves. So that's an experiment that on the one side shows that you have these resonance curves at the operating frequency, and there are differences. Either if you want to read cards from a larger distance, you have a sharp resonance with a high quality factor that enables good energy transfer, and you have damped resonant curves really to limit the energy so that the cards cannot be monitored from far away. Well, now let's go to another type of RFID. Well, that was in fact the first RFID I used in experiments, and on this picture you really see my foot. And what I'm doing there is I'm running a marathon. And if you're running a marathon, you normally get an RFID tag that is supplied by the organizer. And in this tag, here in this longer sleeve, there is a tag that is normally housed in a glass, and they are supplied by Texas Instruments. It's a system that is, I think, more than 20 years old. Same chips are also used for marking animals in houses or so to identify them. All the tags I cover in the presentation are so-called passive tags, so they have no battery inside, and you have to supply the energy from the outside. And now I will have a closer look how this energy transfer happens. And I made a setup that is to be seen here in the lower left picture. So you see the RFID tag here inside a small coil. Here we have the tag, that's a small long shaped rod, and then I have a small coil here that's just a pickup coil to get a good view of the field that is around this tag. And then I have a transmitter coil here. If I would use the transmitter coil at the same time for the receiver coil, I could not really separate the transmitting field and the receiving field, and therefore I use a separate coil. And I power up this coil with the operating frequency of the RFID tag. And here in the trace of the oscilloscope, the first trace shows the time when I power up the RF field. The yellow trace shows the amplitude measured in the vicinity of the RFID itself, and you see it slowly builds up. That simply means you charge a capacitor inside the RFID. And if you have charged it completely, that's about here, then nothing more happens. This kind of RFID tag operates in the following way. So you have first to power it up, and then if you switch off the power, then it will send actively its own identification. And that's what's happening exactly at this time point. The outer supplying field is switched off, but we see still some high frequency signal here. And that is now the transmitted radio frequency signal of the RFID itself. So here for this tag you can really see this is the powering up phase, and then you have a phase where the transmitter is switched off and where only the RFID tag sends its signal. And here on the lower signal you see the demodulation of the signal. In this case it's a frequency modulation, and the microcontroller just looks how long are the cycles of inside this high frequency signal, and then you can demodulate it. and the setup is seen here. It's just an AVR microcontroller. So it's not a special chip. It's really just a normal microcontroller, and then you see here the tag, the coil, the transmitting coil. You see here a resonating capacitor, and in the charging up phase you simply switch on and off the voltage here with the right frequency, and in the receiving phase at this time you simply watch at the voltage at the coil using an analog comparator inside the IC. So it's no special IC, and you can demodulate the signal and recover the information. Yes, that's again an inflow slide where you can read more. Now we come to another sort of RFID that are EM4001 and 2 RFID tags, and they operate a little bit different. It's again possible to build a very simple reader that is shown here on the right picture below the upper picture, and it operates at 125 kilohertz, but at this time this RFID uses so-called load modulation, so that the RFID coil, you can see here, modulates the RFID field, and that's effectively done by simply shorting this coil. If you short this coil, the RFID field will drop, and the reader can try to demodulate the drop in RFID field by simple AM modulation. And that's what you can see here on the left side in the schematic diagram. The power generation for the RFID is again a coil and a resonating capacitor. So these two elements form the basic resonant circuits for power transfer. But then I have to use the same coil to get the information back, and that is just made by a rectifying diode to demodulate the amplitude, and then to watch, can I see that the amplitude is modulation, and then I can detect an RFID. So let's go to a further slide and to see whether it works. You can skip that, and now you see the experiment done with it. In the upper trace we just see a synchronization marker that I can synchronize the oscilloscope, because the load modulated signal is a little bit tricky to catch. This is the RF signal at the reader coil, so it's about 125 kilohertz, and you see that here there is an amplitude modulation.
Yes.
And that is what you have to detect, and that goes into the analog digital converter of the AVR microcontroller. And after the demodulation process, I can watch also the demodulated signal, and I filter it, and then you get these nice curves. For example, you have here in the beginning, you have a sort of preamble so that you can log in with your data clock, and here then start the first data bits. So that's another type of information exchange use that is simply called load modulation.
Is it a reliable system, Martin?
Yes, it's very reliable because normally the tag adjusts to the amplitude, and then it can detect very, very small differences also. There are also, it's a good question as always, normally you also have a phase difference between the carrier and the back scattered signal, and some readers also try to detect this phase difference to increase the signal noise ratio.
Also at such short distances,
yes.
that effect
yes.
happens?
Yeah? Yes, it's just because with the load modulation you change the quality factor of the coil in the RFID, and that gives the phase modulation. It's not because of the distance, but it's because you really change the resonance circuit.
Okay. Yeah.
Well, if you say
Want to
it
build
works
things at home.
it works with load modulation, and we are at a quite low frequency, and then you have the idea to build your own RFIDs, and that's what I did. And that's a schematic diagram, not of a reader, but of an RFID. In the upper right side, you first see our two basic elements, the resonant coil, that's a large coil to detect the supplying field, then the resonant capacitor, And of course, we first have to recover energy to supply our controller. Well, that is a full bridge, and here a smoothing capacitor that gives the energy for the small microcontroller.
So the circuit is excited, or
Yes.
it receives the transmitting energy that's rectified and used as the power supply for the small
Yes.
microcontroller.
So we have no battery inside.
No.
It's really a passive tag.
Okay. You still call it a passive tag, Mark?
Yes, it's a lot of active elements, but
there's a hell of a lot of active elements
But
inside, like
still-
thousands of transistors,
Yes.
but still it's called a passive,
passive
passive
tag.
RFID. Yeah. Okay.
Then I use the RF field also to clock the microcontroller, because when I use the exciting field, I'm automatically in synchronization with the field. So that's
Okay,
very simple. And 125 kilohertz as clock is enough to be fast enough. And the last circuit is that I have a small MOSFET transistor, and I can switch it on and off, and switching it on and off, I can present a varying load for the resonance circuit.
Yes.
And so that's a simple way to make a load modulation.
Pulls the RF energy to ground.
To ground, yes.
Through the
It
MOSFET.
bypasses the...
Yes.
Unfortunately, in these moments, I have no energy delivered to
Okay.
my circuit,
Now,
so you
it
can...
kind of switches off itself.
Yes, it would switch off. So, but the normal regulations or the protocol says is that you do the load modulations only short times, so that you have enough energy. Well, and I tried it, and here in the photo you see a set up, and it really works. And now you can connect different types of sensors to these microcontrollers, and so you can build RFID tags which sensor different things. For example, you can use an analog digital controller, you can use switches, you may even use a Dallas temperature sensor, or you may realize your own unique identifiers for some purposes. And on the picture you see on the left side the RFID reader, and here is a basic circuit, and then you can attach different modules with the different sensors, and you can build all kind of funny stuff with it.
Okay, yeah.
Yeah, so we have a home-built RFID, rectification of power supply, and load modulation by a simple MOSFET. Now we go up to the more complicated RFID tags, and that's an ISO 15693 reader. These kinds of chips are used in many, many different applications. For example, at the university where I work, the local library has every book tagged with such a tag. Many production organizations use these kind of tags to tag the products and to uniquely identify each product in the workflow. And these use a 13 megahertz clock, and to modulate the information onto it, they not only use load modulation, but that at a certain high frequency. So that means, to speak to an amateur radio, to a radio amateur, they use a certain kind of subcarrier.
Subcarrier, yes.
And the subcarrier is about 400 kilohertz away from the main carrier. And now I will go shortly into some details. Well, the first is, again, at this point in the schematic, you see again a coil, that's a reader coil, and again here a resonant capacitor. That's same time as ever. Then we have a rectification here. And the rectification after the first resonance circuit that recovers the auxiliary carrier, the subcarrier. And then I have a tuned amplifier, a selective amplifier that is tuned to the subcarrier frequency. And after the subcarrier frequency, I have another rectifier to demodulate the amplitude of the subcarrier. The use of a subcarrier gives you much more signal-noise ratio, because now the information is really on a different frequency than the power. You transmit the power of 13.56 megahertz, but you retransmit the information on the subcarrier. So you can really keep them away, and let's see how that looks in a real-world test. Well, I made a reader built by this. Again, you see here a microcontroller, here's the analog circuitry, and here's a reader coil with a small tag attached. Well, I told you much about a subcarrier. Let's look at it. That's what normally or often RFID reader books not cover, but that's a look at really at a spectrum. So I looked at a spectrum analyzer into the energy, and the auxiliary carrier is made by dividing the main carrier by 32, and that gives a frequency of about 400 kilohertz. And here in the spectrum analyzer display, you see the main lobe, the big peak in the middle.
Okay. Yeah.
And then you see at a certain distance here, you see additional peaks, and that are the subcarriers. If you remove the tag from the RFID reader, the main peak stays there because it's power, but immediately the subcarriers disappear. Yes, and you can also make a little bit another experiment just to see, or you can try to have a look at the subcarrier. And I wanted to show the subcarrier really how it works, and you see on this trace the following made by an oscilloscope. The yellow trace shows you the demodulated signal by the reader. At the reader output you can see this demodulated signal. The blue trace here is a very special signal. At a spectrum analyzer you often have also an output that shows you the intermediate frequency. And then if you tune your spectrum analyzer to zero span, it's in fact a band filter tuned to the middle frequency. Yeah. And you can easily adjust the center frequency and the bandwidth. So you have a spectrum analyzer costing some €1,000 and you use it as a band filter. And that's what I show here. That is the output of the spectrum analyzer, and that is a corresponding high frequency signal. And you can see, you really nicely see how this auxiliary carrier is switched on and off and contains the information. Aha. Well, now, one of the last things I want to tell, what I also do sometimes is make a presentation at my university special for Christmas, and I also use a trick. Yeah. And that is based on your magician's hat on. I have my magician's hat on, yeah. And then I can do tricks with the help of electronics. Well, the trick is really simple. One of the attendants can select a card, and the card is put into a sleeve. The sleeve is put into a frame, and the magician never touches the frame or the sleeve and doesn't know anything. But by deep concentration, he can really show which card it is. That is hidden into a website, and I go to the website and they say, oh, hey. And then it's really the card that has been selected by the reader. And of course, the normal, or if I say it based on RFIDs, everybody at once knows how it works, yes. But if you don't tell it, then everybody
wonders. Magic.
It's magic. So you can also do magic with it. Yeah. Well, that's the basic information that I wanted to cover today. Here at the end you see literature that may be helpful. Also the different standards you can get. They will be later available at Elector or at Element 14. And the last words of the presentations: enjoy the experiments and have fun with RFIDs. Yes.
Yeah, Martin, it's been obvious that the experiments are a bit non-standard. You like working with non-standard approaches, don't you? It's always easy to kind of follow the manufacturer's data and follow the data sheets officially, but the true fun is, I think, and you think that too, I believe, is in sideways experiments. Be a bit naughty, be a bit off the road, off the beaten track.
Be a nerd.
Be a nerd and be inquisitive and see what's inside these little cards. They look quite innocent, but there's a hell of a lot of technology behind them.
And I think that's what's also very interesting in many of Elector articles. You look always inside the things and say, how do they work?
We want to know what's inside.
Yes.
and we tell our readers. Now, if the Patrick, can you go to the camera, please? We have the happy occasion of showing you a book which is due out in like 3 weeks or so from now, which has very deep technical details on RFID. It's a very thick book. It's like 400 something pages. I've done the editing and the production. And look on the elector.com website to see announcement on this book. This goes deep into the technology.
And one of the authors, Mr. Schalk, is really an expert and is one who works at Philips and knows a lot of RFIDs that you cannot get from other people. So
Okay.
it's really interesting.
It's really in depth. And also I can confirm that it is partly experimental too.
Yes.
There are some things in the book which I'm sure manufacturers would hesitate to publish.
Yes.
about their RFID. So watch electro.com or your .post newsletter, and you'll see the announcement of the publication of this very thick Bible, we call it, of RFID. Now, Martin, let's open the Q&A
Yes.
box and see if we have any questions. Let's have a look. There is Jose Puga here from, I don't know which country.
Yeah.
He's developing a hospital cabinet using UHF RFID. It's a mathematical model to describe the wave propagation. The question is here.
Yes.
Yep. Mm-hmm. What kind? Do you have an idea about UHF antennas?
Oh, I would say I'm not the expert for that, because that's really a question about wave propagation.
Okay. So in the beginning already.
I think there, if it is a what is a cabinet? If it, I think there are possibilities to model that. Mm-hmm. But normally in modeling electromagnetic fields where the wavelengths may be comparable to the geometry, and that is probably the case in your application. Okay. It's normally quite difficult, and you should really try to make measurements also to test your modeling.
Okay, fair enough. As I've said, we'll discuss and get back to people who ask questions in writing after the webinar.
I will try to give answers, or at least hints where you can get answers afterwards. Okay.
Let me have a look. There's a question from Avishek Hardin.
Yeah.
Hello, he says, thank you Avishek for joining. Hello, what's the operating voltage of an Atmel microcontroller? So that is in response, Martin, to having the energy excited and rectifying how far does it go down?
That's for example, the microcontroller I have programmed it that has a brownout detection of 1.8 volts.
1.8.
And if the reader is quite near to the field, I have about 5 volts, and then it drops as I go away, and so I can bridge just 5 centimeters or so. But there was also an interesting or a short question here. So you use a capacitor in combination
Robin G.
to create a resonant circuit. Do you place this capacitor in series or parallel to the coil, and why?
Okay.
And the answer is yes and no. The problem is sometimes for me to, if you have a circuit, really to tell is it a parallel or is it a series circuit, because it sometimes means do you look at the voltage or do you look at the current, and how do you operate it. So it may in fact be that for the transmitting mode you would describe the circuit as a series resonant circuit.
Okay.
And for the receiving mode, you would better describe it as a parallel circuit. Okay. It depends a little bit. Okay. And also, if you watch at the equivalent circuit, the transformer itself has already 3 inductors. And then you have 2 capacitors. And then you can pose the question, which capacitances resonate with which inductors.
Okay.
There are many possibilities.
Complex constellation.
It's a very complex constellation.
Yes.
And sometimes you have to have a closer look, and then you can speak about parallel or resonant, series resonance.
Okay. What else do we have? Do we have?
Well,
more?
let's
The blue
let's just
Okay.
do the blue one.
The blue.
Is,
Yes.
is there
Sorry.
a standard protocol for RFID? The problem is that there are many different protocols, and there are many different ways to send and receive the bits. There are different kind of cyclic redundancy checks, CRC, as you mentioned them,
Yes,
involved.
yes, yeah.
And the problem is that you really have to go into each specification as its own, and you have to normally or a lot of specifications are obtainable on the internet, and in the last sections you also find sometimes sample messages where you can say, okay, if you want to code this message, you have exactly to do this, and the CRC bytes have to look exactly like this, and that's also always a lot of puzzling until you are right. In a normal RFID reader IC, all that is done for you. But if you want to do it for yourself, as I often like, you have really, for each kind of RFID, you have to go into the details again.
Yeah. So we have another one, Martin, from Shirish Kurdi. Thank you. How do you exactly power the microcontroller without external supplies you used in one of the experiments you showed?
If it's about 125 kilohertz tags, I really use the voltage generated by the receiving coil.
Yeah.
And then I rectify it and supply this energy to a capacitor. So
Okay.
in a more normal standard way.
Okay, that's great. Here's another query from Elena Calvo. Thank you, Elena. Congratulations on the webinar.
Thank you for
Thanks for being with us.
Yeah.
Her question is, what's the difference between ISO 15693 and the 1443? Basically, Martin.
Basically, I think for me there are two big differences. I think the second standard, 14443, is more security related.
Okay.
So for identification, for paying methods, so there are also cryptographic protocols involved if you go to the software side. So if you have applications with high security demands, normally these types of RFIDs are used. And the first standard is used in many simple applications with not so high security demands, just to tag things, to identify things, to store a little bit of information, where the damage, the financial damage, is not so big if something happens.
So secure applications, that's the key word. Yeah. This may be a favorite one for you, Martin, from Avishek Hardin. Are there any health risks associated with RFID? Here we go again.
Here we go again. Well, Jan, have you seen changing me in the last years, or do you think I'm still healthy?
I still you think you're a very capable presenter, and I don't think you've taken any damage from your RFID experiments.
But to be honest,
okay.
I think you have to
field
ask
strength are we
the
talking
experts, because the field strengths may be quite big. And if people are concerned about health risks, you have to worry about that, and you have to take care about that. And therefore, I would suggest we should ask the medical experts and the radiation experts, and we should say, use this technology only where it really makes sense.
Okay.
Just to avoid any risk if you don't like it.
Yeah. Okay.
Then the next one seems also interesting. Let's see. I need to attach an RFID tag to a metal case. It does not work, and I need to remain some distance between the tag and the metal case. What is the minimum distance? I'm not an expert for that question, but the normal problem is if you try to attach an RFID tag to a metal case, that you have the magnetic field extends into the metal case, and then you have eddy currents into the metal case, and the eddy currents produce losses, and the losses immediately reduce the the field strength to a level where you cannot detect the tag. But you have also tags that are attached to metal cases, and you wonder how do these people do it. Normally then you have a special layer between the RFID and the metal case, and that is a ferrite.
Yeah.
And with a high frequency ferrite material, you can guide the field through the ferrite, and the field will not extend into the metal case, and then you will not have eddy currents, and then that means you can probably detect the RFID. But it's not such easy.
Okay. Perhaps one final question, Martin, before we sign off.
Oh, well, the last one is perhaps also interesting.
It's
Are there
from,
any security worries when using RFID in ID cards containing personal data? How easy is for someone to steal these data from your personal RFID card? That's also a difficult question, but let's tell me one short story. The University of Aachen, the big one, introduced the student ID card, I think 2 years ago. And 2 weeks after rollout of all these cards, there was a severe security fault detected, and all these cards had to be collected back and new cards had to be supplied. It was not the technology of the card or any fault in the protocols involved. It just was that the software used and the technology was not used in the intended way. So it was an implementation fault. So as long as humans and the implementation authorities make errors, there is always a sort of probability that someone can steal it. Yeah. So what I would like is if all these standards are often and all are open, and all reader software and all things should be open, so that you can contact any authorities you want and can say, can you prove that this protocol is really secure? It must be checkable by the inhabitants of a state that it's a secure technology. It's not a good way to hide the security. There is a standard saying that says, security by obscurity is impossible. History has shown that. Every time a cryptographic protocol was based on obscurity, it has been reverse engineered within a short time. So I think security should be based on open protocols, open standards, open implementations, so that everyone can check that it's really secure.
Okay. Great, Martin.
Okay.
I think we have the questions and answers box closed for the moment, for the immediate discussion. And as I've said before, we will answer everybody in writing, and the answers will be posted at the Element 14 website for everyone to review later, as well as your special slides in the presentation. There are self-study slides with massive information, literature, background, and further experiments, as well as Elector magazine references.
Yes, also, of
there
course.
is a ton of information on RFIDs published in Elector magazine in the past, already from Martin and other contributors, with very nice and some very out of the ordinary experiments, if you like. That's what Elector is all about. I'd like to close this session, Martin, by thanking you very, very much for a brilliant expose for this afternoon, with lots of technical details, and again, you know, a sort of inspiration to try and go into the experiments. That is the main message, I think, of this afternoon. Don't be afraid of a technology that's presented to you as if it were law or writing or what have you. Open these things, get to work with them. The technology behind is very exciting.
Get your hands dirty.
Get your hands dirty. My hands are still very clean, as you can see, but they will be dirty by writing and about these items, and you, of course, contributing.
Yes, and thank you for all the attendants for watching the show.
Yeah. Emily, back to you at Premier Farnell, please.